Okay, let's get started on some numerical practice for balanced forces. So here's our first example. 45 kilogram box sitting on a table. Draw a free body diagram. Find the value of the forces on the block. Okay, so I am going to just draw right on my picture here. I think I'll choose red. That's a good one. All right, so coming down, we're going to have force of gravity. Hopefully you know that you've got to have a normal force going up. And if it's just sitting on the table, there we go. We're balanced, right? We can't have friction because if we just had friction, say going that way, now we're unbalanced. Now the block has to be changing its velocity. So that just can't be there. All right, we just have Fn and Fg. Now the thing about balanced forces, when we start to work with them numerically, the main things that we keep in mind is that all the forces pointing up have to equal all the forces pointing down, right? And then all the forces going to the left have to equal the forces going to the right. Now, as you can tell, I don't have any forces going to the right and left, so that kind of is a moot point, but it still has to, be satisfied. This is going to be the one that we spend the most time taking a look at. So, what can we figure out from up and down? Well, down is going to be gravity, and up is going to be normal force. So these two have to be equal to each other. And if I want you to find out the value for those, well, we're going to have to work with this. All right, so the 45 kilogram mass, how that's going to help us is we know we can find Fg by doing mass times little g. So if I do 9.81 times that 45, that's going to tell me the value for Fg. All right, so we've got 45 kilograms and then 9.81, either newtons per kilogram or you can use meters per second squared. It doesn't matter. It's the same thing. You're going to see meters per second squared a lot more. And we're going to get approximately 441 newtons for that. That's going to also be the value for F sub n. All right, so that's all I really need for that one. Just wanted to find both. All right, here's our next one. Same 45 kilogram box. That's nice. I'm going to write down right away the value from the last question, 441 newtons, so I don't have to recalculate that, okay? All right, I push at a box with a force of 100 newtons, yet the box doesn't move. Draw an FBD, find the value of all the forces on the block. Okay, well, this is going to be a force normal going this way because I'm crunching on the box. I know we have to have Fg because we always have Fg, and which means we're going to have a responsive force of Fn. That means we've got to have, if we're not moving, we're still at constant velocity, there's got to be a force going this way. Now, typically, I wouldn't draw it like this. Typically, I would draw it like this. But you know what? It doesn't really matter, truthfully. But now this normal force, this is going to be from the table. Right? We know that this Fg is from the earth. This normal force is going to be from the hand or whatever's doing the pushing, right? This one has got to be friction. That's a shearing force trying to stop it or hold it back. It's not moving. We could be more specific and call it static friction, but we don't really even have to. All right, so this is going to be from the floor as well, or the table. Sorry, I called it a table at one point and then I call it a floor. It's really a table. That's okay. All right, find the forces or find the value of the forces on the box. Well, luckily, I already know Fg because that's from the previous question. So if up equals down, these have got to be the same, right? Now, here's the other thing. It tells you that left, or the force of the hand is 100 newtons. That's given to you right here. Again, if we're dealing with balanced forces, now the whole left and right thing has to come together, right? So this is going to be my 100 newtons of friction because I have 100 newtons of force over there. So Fg is going to be 441, Fn is going to be 441. My second Fn, or maybe I'll call it Fn number 2, is going to be 100 newtons, and my force of friction is also going to be 100 newtons. So there we go for that one. Now we're going to start getting a little bit trickier. Okay, so still a 45 gram box or kilogram box. So again, I'm going to be a little bit lazy here and not recalculate it because it's the same as the last question. All right, we're pulling with a rope with a force of 100 newtons at 25 degrees to the horizontal. Draw the FBD, find the value of the forces on the block. Okay, so we are moving. We're moving with a constant velocity. All right, so we've got to have FG going down. We're going to have normal force going up. This one is a tension, right? And so let's think about that one first. It says here that it's moving at 25 degrees to the horizontal. That means we can take this diagonal tension and we can break it up into what I like to call TX and TY. I think that helps me out quite a bit. I know that it's part of it, but I also know that they're not really the same thing as the tension. Okay, so this is my opposite side. This is my adjacent side. And of course, that's my hypotenuse. And this is where my 100 newtons goes, because that's how I'm pulling it. Okay, so I can figure out Tx and Ty. And if even without doing the math quite yet, if you know this is moving with constant velocity, like it says, there's got to be something going this way, right? Because this can't be all by itself and have it balanced, because left has to equal right. So again, we've got to have friction. Otherwise, it's not going to work. And here are some of the key things, right? So if I figure that, forces going up have to equal the forces going down. Let's look at our diagram. What's pointing up? Normal force is pointing up. Ty is pointing up. What's pointing down? Fg. All right, so that's going to be an equation that I use to help me out. And then if I do left and right, okay, so forces left equal the forces to the right. What's pointing to the left? Friction. That's got to be equal to Tx. That's going to be the next thing that helps me out. Okay, so I'm going to do the math over here. Pick a different color, so maybe it'll be a little bit easier for us to see. Let's start with the triangle, because I can figure out a bunch of stuff from my triangle. Okay, so if we have, let's start with sine. Sine of 25 equals the opposite over the hypotenuse, so Ty over 100, because that's my hypotenuse, so 100 sine 25 equals Ty. And I'm just going to do some quick math. You do want to make sure you are in degrees, not in radians. Okay, I borrowed Mr. Hartz's calculator here and messed up my problem before. All right, so this one, Ty, this is going to be 42 newtons right there. All right, I'm going to do the same thing for Tx, but it's going to be my adjacent side over 100 newtons. So 100 cosine of 25 equals Tx. And that's going to be approximately 91. I'm not too fussy about the rounding. Whole numbers for forces usually does the trick for me. All right, so this one's going to be 91 newtons. Now the nice part about that is based on what I already said before, that lets me know what the value of the friction is. The friction's got to also be 91 newtons. So we've got 91, 91, 42. You might want to start just making a nice little list someplace. I still have a little more work to do. So let's see, Tx is going to be 91 newtons. Ty, we've got at 42 newtons. Force of friction, that's 91 newtons as well. Fg, well, we already have that one, don't we? 441 newtons. That's nice. Now let's do the other one. Let's do the up and down. Okay, so let's pull that one over here. All right, so Fn plus Ty equals Fg. The only one we don't really know is the normal force. Now you might want to say, oh, well, these two have to be equal to each other because they're both going up and down, but not this time because of this little guy right here. It's going to mess things up. So we're solving for Fn. So I can take Fg and subtract away Ty for that. Okay, so Fg, we have 441 newtons. Ty, we've got 42 newtons. This is going to give me my last one, which is Fn. Let me just do a little bit of quick math here. And I got a normal force of 399 newtons. All right, so that's our last one right here of our little list. Ta-da! There they all go. All right, when you have something with being pulled at an angle, you're going to take that and make it a triangle every time, okay? And draw me some arrows, not sticks. That's important. All right, if you are moving up this way, that means you had to have been going to the right. Make sure there's an arrowhead, and you have to be going up. So make sure there's an arrowhead. That way you'll be able to tell what's pointing up and what's pointing down. Otherwise, that is going to mess you up. Okay, this might look just like the box, but don't be fooled. Can you tell I don't know how to do a lot with clip art? All right, so a 500 kilogram lawnmower, and it's being pushed. You're pushing it across the lawn at a constant velocity with a force of 200 newtons. The handle makes 30-degree angle to the horizontal. Draw the FBD. Find the value of everything. Okay, so let's do our free body diagram first. FG. Normal force. Again, you can probably guess that we're going to have friction involved here, but let's start with we're pushing this way on the lawnmower. That's a big deal. It's not pulling this time. All right, so 200 newtons, right? Which means, again, when I do my triangle, be careful. You got to go down and you got to go over. All right, you're not going up this time. You're going down. All right, and this is a 30-degree angle. This is a 30-degree angle with the horizontal, okay? So make sure you read the question carefully as to where that is going. Okay, now in other forces, as you can see, if I have something pushing to the left, but I'm moving with a constant velocity across the lawn, I've got to have friction, and it's going to be going that way. All right, so again, what do I want to know? I want to know friction, I want to know normal, I want to know gravity, and I want to know, I don't know, T, well, technically it's a normal force in the X and in the Y, because we're pushing, right? Now, this is the first one I can figure out, right? Because I know that that's M times G. So I did that one. I did 500 kilograms, and I know that I need to do this because it's not already in newtons per kilogram, right? So I got a value of FG of 4905 newtons. All right, easy peasy. Next, I'm going to attack my triangle. All right, don't be fooled into thinking you can just label the normal force at the same as gravity, because it's not. You're going to have this. All right, now this is a normal force. We'll call that normal force number 2. All right, so we'll say these should have little number 2s with them as well. All right, so this is going to be normal force 2y, and this will be normal force 2x. All right, let's figure out our triangle, because that's the next thing we can figure out, right? So again, SOHCAHTOA, this one's going to be my sine function. So sine of 30 equals opposite over hypotenuse. Luckily, I know the sine of 30 is a half, so I don't have to actually punch the calculator for that one. Yay! All right, so that one's 100. Excuse me. 100 newtons. 100 newtons. All right, next one is going to be the cosine function. Cosine of 30 equals f into x over 200 newtons. So I'm going to multiply 200 times the cosine of 30. Fn x2 is going to be 173 newtons. Okay, so that's 173 newtons this away. Sorry guys, I'm trying not to cough, but I've been talking a while. All right, so hopefully you were seeing left equals right, up equals down. All right, so let's change colors because this green kind of gets on my nerves. Let's go back to red. All right, left equals right. Fn2x has to equal the force of friction because left equals right. Right, and that's pointing to the left right here, and this one's pointing to the right. So those two have to be equal. This tells me that my force of friction is going to be 173 newtons, just like this one is. Now let's do normal force again, because we have more than one arrow pointing up and down. we have to do a little math with this one. All right, so everything pointing up equals everything pointing down. And what's pointing up? Normal force. What is pointing down? Fg and Fn2y. So in this case, we're going to add it together. We're going to take our 4905 and we're going to add on 100 newtons for each, right? And so Fn is going to be what? 5. Oh God, I can't even do math. I am so tired, you guys. Good grief. That is pathetic. Okay, so there's Fn. Hopefully you're getting the idea of up and down, left and right. Let's see what else we got. Oi, I got one more. Oi, I really got one more after that. Okay, let me, let's go back to this one. Okay, this sign hangs in your favorite coffee shop. All right, I'm going to pause for a second and come. All right, so I went to town on this worksheet. There's a whole lot of questions here. Alrighty, let's do this. 2 upper chains make 30-degree angle with the ceiling, top placard, bottom placard. Find the tensions in all 3 chains. Okay, when you work with objects that have more than one object or more than one body in them, what you should really do, let's call this one number 2, let's call this one number 1. You should do them individually, okay? I'm going to start with the bottom and work my way up. That's going to be easier for me. And this is suspended, which tells me that all the forces have to be balanced because the velocity is 0. So here's number 2. Let's think about this. What's pulling it down? Gravity. What's pulling it up? Tension, right? And they have to be equal to each other. So let's see. The lower placard has a mass of 200 kilograms. This one has a mass of 75 kilograms, and then they each have a 30-degree angle up on the top. All right, so to find Fg here, we're going to do m times little g. So 200 kilograms times 9.81 newtons per kilogram. Okay, let's do that. We get 1962. 1962 newtons, which tells me that this one is going to be 1962 newtons. Right? It's got to be. All right, so now I've got those 2. Let's focus now on the other one. All right, so here's placard number 1. It has tension trying to go down. Right, that tension that we already know is 1962 newtons. It's the same rope. It's pulling up for the bottom placard, but it's pulling down for the top one, right? Because it's going the other way. Now, we also have Fg for number 1, but it's over. I'm putting it over to the side because I'm running out of room. And then I've got these 2 tensions, right? So tension, well, I guess we call that 1. This one will be 2. This one will be 3. Okay. Now it says here that these are both 30-degree angles, which is handy. That is handy for me to know. What that tells me is that T2 has to equal T3. I mean, I don't know what they are, but I know they have to be equal because they have the same angle going on there. Okay, so here's how I'm going to look at this. I'm going to use my triangles again. All right, I'm going to work on the outside because I think I'll have a little more room. All right, but I'm going to go out and up. I'm going to go out and up. If this is a 30-degree angle, this is a 30-degree angle, and so is that. All right, so I know that's 30 degrees. That'll be perfect. Okay, now let's call this Tx, Tx, Ty, Ty. And the thing is, since the angles are the same, I know that these have to be the same, so I'm not going to give them numbers like 2 and 3, because it's kind of a silly proposition. Okay, now, let's remember the premise of balanced forces. The forces going to the left have to equal the forces going to the right. So ask yourself, what's pointing to the left? What's pointing to the right? Oh, Tx. Tx is pointing to the left. There's another Tx pointing to the right. Well, that's nice. And I know they're the same. Okay, big whoopee. So I've got nothing mathematical here, but that's okay. Let's look at the bigger picture. Let's look at up and down, and I'm going to move all the way over here because there's a little more to this one. All right, the forces up equal the forces down. So ask yourself, what's pointing up? Well, I have this and I have this, two TYs, and I know they're identical, so I'm just going to put them right there. What is pointing down? FG and T1. Okay, so FG, this FG1, because it's for block number 1, and T1. Okay, well, the good news is that I know T1, and I know, or I can find FG1. That's not so tough. So let's do that next. I'm going to change colors again to try to make it a little easier to see. All right, so let's do the easy one. Let's do FG1. FG1 is going to be equal to 75 kilograms. That's 9.81 newtons per kilogram. All right, so when I do this, I get about 736 newtons. Okay, so that is going to go right there. And then T1, which I already know, which is 1962, that's going to go right here. All right, so what I'm going to get, let me go back to my original color of red. I'm going to get 2TY equals 736 plus 1962. And I'll slap some labels on those. All right, so plus 1962. .2698 newtons. So I divide by 2 and I figure out what the value of Ty is. I get approximately 1349 newtons. Okay, so what this tells me is I know the value of this and of this. Why is that helpful? Because I'm going to be able to figure out the hypotenuse because I know an angle and I know the opposite side, so I can use trig and I will figure it out from there. Okay, so back to a new color. Let's talk about that triangle, right? Because right now, let's see, I've got this one figured out. I've got this one figured out. I've got this one figured out. I just need to find this one right here and that one right there. And my question is finished. Okay, so Ty is 1349. Let's just take a look. Let's just use the right side triangle. All right, so this is 1349 newtons. This is a 30-degree angle, and this is T. And I know that the two T's for each of the triangles, they're identical. All right, so this is a sine function. Sine of 30, because it's an opposite side, right? Opposite over hypotenuse. T sine 30 equals 1349. T equals 1349. I'm running out of room. Divided by sine of 30. So essentially, it's times 2. Tension in my rope is going to be 2698 newtons. All right, and that is for both of them. So there we go. It's messy and I'm out of room, but hopefully you see how you find all your little guys there. All right, next, last one. Oy vey. Okay. You know what? I am going to say, let's see if it's at rest. All right, I see how we do this one. This one is a super tricky one, but it's a good practice. Okay. How long have we got here? 25 minutes. All right, let's do this one. If you've got a two-body system, what you want to do is do one of each. All right, so here's our hanging block. All right, we've got FG for the hanging block. We've got T for the tension of the rope touching the block. All right, this is going to be MG, and we know that it's 6.5 kilograms times 9.81 meters per second squared. Okay, so 6.5, 9.81, approximately 64 newtons. All right, that makes tension 64 newtons because up equals down. All right, now let's do the free body diagram for the triangle. That's the part that's going to be a little bit trickier. Okay, I am going to be totally crazy, and I'm going to do it here. All right, we're going to have tension. We're going to have the force of gravity, or mg. We're going to have normal force, and then there's going to be a friction force, but I am just going to let friction be for a little while. Okay? Now, and I'll explain why in a little bit. All right, so when I have triangle within a triangle, whoops, I put my hand on this, so let's see if that'll do. Okay, you're going to do the triangle within the triangle when you're doing a problem on inclined plane. This is a 35-degree angle. It matches whatever is over there. This is going to be mg sine of theta because it's the opposite side. This is going to be mg cosine of theta because it's this side over here. Now, when I only focus on block number 2, the first thing I'm going to say is, okay, lifting off the inclined plane, like lifting this way or sinking this way. That's not happening. So I know that the normal force has to equal the mg cosine theta side. All right, so that's an easy way to figure that one out. So how much was the block? 7 kilograms. Okay, so 7 kilograms times 9.81 for meters per second squared, or newtons per kilogram, cosine of 35. That's going to give me the normal force. So hopefully you can read my getting messier by the minute handwriting here. Cosine of 35. All right, this is going to be 56 roughly newtons. All right, so that's my normal force going up. All right, that one's pretty straightforward. Now, let's talk about the forces trying to go this way, either up or down the hill. These also have to be balanced, right? So let's think about this. Up and down the hill, we've got, I know that tension has got to be opposite. Actually, let me rephrase. Let me start over. Forces up the hill have to equal the forces going down the hill. Okay, going up the hill is tension. And I know the value of tension, it's 64 newtons, right? What's trying to go down the hill? mg sine of theta. All right, let's figure out what the heck mg sine theta is, right? So what do we have here? 7 times 9.81 times the sine of 35. Now you notice I'm not just assuming that they're equal. There's a reason for that. Okay, remember we didn't do friction? That's because I wasn't sure which way it was going to go, and this is going to tell me which way it goes. So once I type the numbers in correctly, I get 39, roughly 39 newtons over here. Well, this is obviously not the same thing, but they need to be equal because, again, it's at rest. So that tells me that the force of friction's got to be over here because it's going to make up the difference between the two. So if I subtract them, I get 25. So 25 newtons has got to be the force of friction. Whew, that one was tricky. It was tricky, but it wasn't too bad. All right, so hopefully all of that makes sense. Let me just, all right, let me write these down. So Fg for number 1, that was 64 newtons. The tension in the rope is 64 newtons. The normal force worked out to be 56 newtons. And the force of friction, those are the biggies, 25 newtons. Now, I'm not saying we didn't need to find this one and this one, but when you're figuring out what your actual forces are, that is, oh, I probably should do Fg too because we never did that. That's the block sitting on the hill itself. I never even actually found that one. All right, this one's about 69 newtons. And we got a list now, but all the work is there to show us where they came from. All right, so that is some pretty detailed practice. There's quite a bit in there, all different types of physical scenarios, friction, no friction. But the main thing when you go to solve these problems, the key thing to remember is left equals right and up equals down. So hopefully you found this helpful.